We trust modern blockchains to secure billions across decentralized networks. Yet beneath the cryptography, the logic executing those transactions is structurally brittle. The computational DNA powering almost all of Web3 dates back to the early 1980s. Deploying a smart contract on Ethereum or Solana uses an execution model mirroring Tim Patterson's QDOS, the exact single-threaded architecture that became MS-DOS. This 40-year-old architectural choice is the specific reason Layer 1 and Layer 2 blockchains repeatedly fail to scale composable applications. The scaling crisis originates in an operating system bottleneck, an architectural defect from the 1980s that persists regardless of networking speed or bandwidth. An MS-DOS program uses a single flat address space. Code and data share the exact location, executing through a single entry point. Now observe this smart contract state tree. The structure is identical. It unifies bytecode and persistent storage at a single global address. Both systems are strictly passive. They sit inertly until a transaction arrives, triggering a synchronous blocking action. When a smart contract calls another contract, the caller halts and waits for the receiver to finish. This visualization illustrates a single instruction, single data, or SIST environment, where only one operation alters the global state at a time. No matter how many thousands of users interact simultaneously, every transaction is forced into a single sequential queue. Because execution relies on a strictly last-in, first-out call stack that pauses the parent function, attackers can hijack the sequence. This synchronous blocking is the structural cause of reentrancy attacks. Co-locating code with shared mutable state throttles execution speed and creates an inescapable serialization bottleneck for every user on the network. To fix this capacity limit, developers attempt to shard the network, splitting the workload across multiple parallel nodes. However, splitting a shared global state is impossible without breaking the logic. This forces smart contracts into a strict two-mode dilemma. In Mode A, contracts are deployed completely independent of one another, sharing no data. Mode A scales efficiently across shards, but it breaks composability. Tokens and contracts cannot interact across shard boundaries without massive friction. Then there is Mode B, where contracts actually compose. They interact by calling each other through the shared external state. This graph illustrates Amdahl's law. The speedup of any parallel system is bounded by operations that cannot be parallelized. As nodes wait for shards to process shared state contracts, dependencies stack up. Eventually, the parallel network degrades into a single, highly congested sequential line. Adding more shards to a shared state architecture only multiplies the bottlenecks. Generalized composable scaling is mathematically impossible within the smart contract model. The solution to this shared memory problem was engineered in the 1970s at Xerox PARC. Computer scientist Alan Kay recognized the inherent limits of procedural programming and engineered a new model, Smalltalk. Kay's architecture relied on encapsulation. Encapsulation dictates that every object must own its state exclusively. There are no shared global variables allowed anywhere in the system. This diagram shows independent cellular objects. Because objects cannot reach into one another's memory, they can only interact through asynchronous message passing. Instead of a synchronous function call piercing another program's logic, objects send distinct packets of data and move on. The system uses extreme late binding. The receiver of the message decides exactly how to compute it at runtime, decoupling the instruction from the data. With local state and message passing, these cellular objects operate concurrently. Thousands of interactions occur simultaneously without central queuing.
By destroying global shared state, Kay's model allowed autonomous components to compose naturally without requiring centralized coordination overhead environment. This comparison illustrates the structural difference. In SagaChain, smart contract addresses do not exist. Code and state are unified directly inside the individual user's account. User account objects send peer-to-peer messages directly to other user account objects. Because there is no shared external contract to hijack, and interaction happens strictly through message passing, re-entrancy vulnerabilities are structurally impossible. Developers don't deploy standalone bytecode. Prasaga uses an on-chain class manager infrastructure managing all objects globally. This hierarchical structure represents the global class tree. Accounts dynamically inherit logic at runtime from this single tree, pulling behavior down into user nodes exactly when messages are received. Moving code to a shared global tree, while isolating state inside encapsulated accounts, decouples execution from data storage. This structure enables parallel execution that shared state systems structurally cannot achieve. Even with encapsulated objects, assigning transactions efficiently across parallel shards is considered an NP-complete problem in general computer science, meaning it is a mathematical puzzle thought to be computationally unsolvable at scale. This brings us to the Biberman conjecture. It argues that the sharding assignment problem is only unsolvable if you assume network transactions are completely random. This graph starts as a chaotic web, but real-world blockchain transactions are never random. They represent structural human economic relationships, like supply chains, payrolls, and recurring counterparties. These transactions naturally form distinct, dense clusters of activity. These relationship clusters are temporally stable. While the probability of two accounts interacting decays over time, it is highly predictable in the short term. Blockchains map human economic behavior. Because the exbiome exposes this underlying relationship structure, those clusters become mathematically exploitable. SagaChain uses a mechanism called SagaScale to track these exact relationship probabilities in real time, predicting colocality. It actively draws temporary shard boundaries around related accounts before they even execute a transaction. Because all state is entirely local to those group accounts, they compose with zero cross-shard block dependencies. This model achieves multiple instruction, multiple data, or MIMD parallelism. MIMD is your execution paradigm where separate processors handle different data using different instructions at the exact same time. By predicting and grouping economic relationships, SagaChain bypasses the cross-shard communication tax that chokes traditional networks, offering a practical solution to an NP-complete assignment problem. To make this function across a physical network, Prasaga adds a crucial innovation to K's model, the Single System Image, or SSI. The SSI synchronizes memory transparently across all distributed nodes. While programmable smart assets handle the logic, operating a trustless network requires a unified economic foundation. All transaction fees and value transfers on the network settle exclusively in SagaCoin. This singular settlement layer eliminates the fragmented multi-token fee markets that plague other ecosystems. Instead of patching an overwhelmed architecture with Layer 2 workarounds, execution and settlement occur at the base layer. The scalability limit of composable blockchains is a structural defect inherited from MS-DOS. By abandoning shared mutable state for encapsulated message passing, decentralized parallelism becomes a functional reality.